Hello, we are going to explore very important concept which we are addressed earlier too, like instruction set architecture. We know that instruction set architecture is essentially the language of CPU, and it defines the instructions the processor understands, like moving data, performing addition, subtraction, multiplication, for a while controlling program flow. To make this more concrete, let us try to understand it through simple C program, which can be compiled and down into instruction set architecture level instructions using GCC. And I'm using this GCC compiler on Ubuntu operating system. Let us start with a very simple program in C, just some arithmetic operations, no loops, no conditions, and this will help us to understand how basic operations are mapped directly to CPU instruction. So let us start. So say we are giving name to the program as program1.c. So let us type the code. So we'll write in main. Before that, let us add hash include stdio.h because we want to make use of printf over here. We'll declare two variables, integer a equal to 10, b equal to 8. Fine. And then we'll declare three variables, like first is sum, which will hold addition. Second one is difference, which will hold subtraction. And last one is product. This will hold multiplication. So let us write sum equal to a plus b, diff equal to a minus b, and product is equal to a multiplied by b. Now, as the result is computed, let us say, so we have to print the values. Result is sum equal to %d, difference is equal to %d, and multiplication is equal to %d, then slash n, then the variables sum, diff, and product. So this is done. Now we'll write return 0, curly bracket complete. Now if we see, like we declared here two variables, okay, integer a and integer b. These are two numbers, and we are computing or calculating their sum, their difference, and the product. And finally, we are printing the result. This is what the program is. So let us save this. Let us compile this. So let us compile. So we'll use GCC program name.c. Okay, and then we'll print executable like with myXC as a name by writing -o. Now, once this -o gets this executable is created, we can execute it. So our executable name is myXC. So one can see that the code, whatever the code that we wrote, the output we got is result is sum equal to 18, difference equal to 2, and multiplication equal to 80. So far, this is just normal execution at high level C program. Now comes the interesting part. Instead of running the compiled code, which is like linked to, let's ask our compiler to generate the assembly code, which is very close to instruction set architecture of the CPU. Now, how do we generate the assembly code? So let us write GCC, then you write capital S and your program name. So say 1.c, and again, like if you want, okay, we will generate only assembly code. So you write -s, it will generate assembly code. And this produces a file, like if I write ls-ltr, okay, so if you see the last line is this one, 1.s. Okay, with ls-ltr, if we write last one is 1.s. So let us try to display now the simplified snippet. Okay, like let me open this, say less 1 dot s. Now there is huge code added in assembly language, and this is actually the file created with an executable file format as x86 64. On what basis I am saying this? So we can make use of a command called file, okay, which can be used to really find out what exactly the executable is. Say if I write file a dot out, then it shows me, okay, so we'll create it, the executable. Okay, so let us create my exe. So we'll write file my exe because this was our executable. So one can see here the output. What is shown here is it is saying it is an ELF executable and linkable file, 64-bit LSB PI executable. Okay, and like the instruction set architecture used by it is x86 64. Now suppose like this machine or operating system that I'm using is a 64-bit operating system as well as 64-bit architecture. Now these instruction set architectures should support the backward compatibility too. So if I want to create, say, this assembly code like what was shown here, this was with respect to a 64-bit architecture. If I wish to show it with respect to say 32-bit architecture, then I have to just write here control R GCC dash capital S. We wrote 1.c and then write dash M32. Now, if you want to create a 32-bit executable or an object code, you will require multi-lib library to be installed. So right now, what I'm doing is, okay, I will remove these dashes and I will create executable just with 32-bit one. So dash O and then file name. So file name is my.exe. Now, once we created earlier, it was showing us this output. Okay, what the output that was seen by us, like this one, correct? Now, if I write again same command like file, then one can see now it changed. The output currently is showing us now. This is a ELF, again executable and linkable file, which is 32-bit LSB PI executable. And it is now showing us that it is making use of a 32-bit architecture like 80386. This is instruction set architecture that it is trying to specifically add here. Now let us try to create an assembly code. Say first of all, we'll try to create that assembly code with 64-bit. So now when we already know that when we do talk about instruction set architecture, ultimately there are multiple components and one of the component is registers. Okay, so I will not write anything. So as we know, if I write, if I display that file, this is a huge code that is generated. Now it is adding some things over there which are internally added by your compiler. Okay, while creating an assembly code. Now the most important for us to understand is this one now. Okay, let me elaborate on that. Okay, now what exactly we are going to exactly check over here. So let us try to see like we had, suppose if I open another window and if I show you the code less but not C. Now you can see that we have a variable A and we have variable B. Values are 10 and 8. Correct. Now if I try to check them, so they are here. $10 and $8. And this RBP, like this is the register, base pointer register, 64-bit register. So both of them, like the on the stack rather, these local variables are added. We'll talk about it later, not too much worry about right now. Okay, so these are the kind of assignments that are done. Like when you wrote integer a equal to 10, ultimately it is writing like this, $10 value, like 10 value is given to this, 8 value is given to this. Then if we see, like, so let us talk about sum A and B. So we got these values which are stored there with the base pointer, respective locations on the stack. We are moving them into the registers respectively as EDX and EX. Then both of them are added like using add L. This move L is instruction. Then add L. Here the addition is done, and that addition is stored with EAX. Okay. And then again, that is stored with variable C, variable sum. Likewise, sum equal to A plus B. Similarly, if you talk about A minus B, you should see same thing. Instead of now add, we are going to see subtract instruction. Again, the result is stored. Then we talk about product, multiplication. It is an integer multiplication. That's why one can see imul instruction used. Correct. Now, if we see this, let us try to carefully understand what exactly is happening here. Mul is the instruction to move the data. It loads or stores values between memory and registers. That's what we are saying. Add L is the addition instruction. Like it adds two numbers. Subtraction at the same time. Subtract, it is a subtraction instruction. It subtracts one from the other. Imul is an integer multiplication instruction. So these all are the instructions that are shown over here. So you can see here like high level operations in C, like for example, in this right window, like sum, addition, subtraction, and product are exactly directly mapped to instruction set architecture level instruction like this, the way we see. Now let us try to go into more details. Now the thing that I showed you before a while, like the file format, which was create or shown for the files. Like for example, if I write my exe here, which was our executable, so it is showing us 32 bits. Similarly, if I create here, this was 32 bits. If I remove this M32, then it is giving me a 64 bit. Correct. Now, this confirms that our object file uses, like in this case, when we wrote a dash M32, it is showing us that it is using Intel 80386 architecture. That means Internet IA32 instruction set. Which this is an instruction set used by the most of the modern Intel and AMD processors, if it is talking about backward compatibility. But if you talk about current modern Intel and AMD processors, each one of them is creating this file format. Like this instruction format, rather instruction set architecture is used to create this file. Now finally, let us try to go into more details now. How exactly the code would be shown. Like if I try to generate, like though we could see this code, like for example, when I wrote this seen to us, this is just an assembly code, but it is not the machine language code generated. Please understand. Now, if we want to see what code was generated, so let me create, say, an object code for a while. So I will write dash C. Okay, let me write dash M32 for a while. So now if I write file 1.0, then this would be a 32-bit LSB relocatable. Now there is no executable written word earlier because if you see here it was showing executable, now it is showing here relocatable. This object code can be fitted anywhere while creating the executable, and that's what it is showing Intel 80386. Similarly, if I remove this and show file format, then it would be same thing, just the instructions and architecture is changed. Now, if I want to see the contents of that object code, so let us say if I write 1.0, then it says it is a binary file you cannot see. So one can try. Like if you write Y, then it shows you. Okay, you can try this definitely. But if I want to really check out what exactly is there, okay, so what can be done is let us make use of a disassembly command, like which is called as obj dump. This obj dump command helps us to know information from the object code or object files or even executable files. And this is where we are going to make use of to see the exact machine instructions, which is written in hex. So let us write obj dump dash d and our file name. So like let us try to target the important things for us, which are important for us. Like for where are they? So these are the ones. 10 is converted to A, 8 is there. So both of the values are stored here. Then we know that there was the addition instruction, correct? And then further addition is done. Then addition is stored with the stack element and so on. Similarly, subtract, then move L and so on. So all such things are carried out by it. And this is the ISA action. Which one? This one. Like here, what you are saying is you are saying the hexadecimal representation of the assembly code that is shown towards right. Correct. So right side would be assembly mnemonics along with the operands. And the left side is containing opcode along with the different parameters that are included into your instruction set. And this is what we say the real instruction set architecture. Every single instruction is what the CPU is going to execute, and that instruction would be like this, executed through this. So to summarize, okay, let me do one more thing. Like here, what we did was we created executable with the 64-bit, and then when we disassembled it, we could see this one combination of 64-bit as well as 32-bit register. If you strictly want it to be 32, just write dash m32 and then check this one. So you will see now there is no 64-bit register used. Each one of the register is a 32-bit register. Now where is our 8 and 10? So these are the two, correct? Then further, like there is addition instruction. This one is addition instruction, then subtraction instruction, and then multiple instruction. So to summarize, what we did was we wrote a simple C code with arithmetic operations. Okay, we compiled it normally to see the output, and we asked GCC to generate assembly, which shows us the Intel, or rather instruction set architecture level instructions like move, add, sub, even imul. We verified the ISA type using file command. For 64-bit, we saw x86 64 written, and for 32-bit, we saw Intel 80386. We disassembled the object file using objdump to see the actual instructions and the opcodes. And this process clearly demonstrates you or us what instruction set architecture means. And one can say that it is a bridge between high-level code and hardware execution model. In next recorded session, would be saying like what happens when there are other than these instructions.